This is the continuation of the previous video. In the last video, I highlighted some of the important features of the ISO15693 standards, and I also highlighted some of the important points from the part 1, part 2 and part 3. In this video and the next few, I'll be discussing the part 3 document in detail, because this is very important for us to understand this document in order to know how the ISO 15693 attacks work. So what you see here is the part 3 of the document, and you can download this from internet. You can also download this from some of the manufacturer's website as well. In this document, you're going to learn the protocols and the commands, and you're going to see how to initialize a WIC and the VCD, and you're going to see different methods of selecting a card when there are more than one card in the near the VCD, and also going to see how to speed up the selection process. So you have to familiarize yourself with these abbreviations. So in the last video we have covered a little bit of these abbreviations as well. The AFI, this is the application family identifier. You know, the CRC, the DSFID, this is the data storage format identifier. The EOF, the LSB, the MSB, and the start of frame, the UID, and the VCD and the WIC. So all these abbreviations are used throughout the documents. So every ISO 15693 tag will have a unique identifier. So using this identifier, you can differentiate from one tag with another. So the documentation says the size of the UID is 64 bits, and all tags which address to this standard must have the 64 bit as a UID. And you have to keep in mind, this document sets the baseline or the minimum requirements of all the tags that conforms to ISO 15693 standard. So most of the definitions here and most of the command structure here, now they will cover the commands used by various tags. So that's one of the reason why I mentioned before, it's very important for us to understand this document. So the structure of the 64-bit is also given here. So you have to get yourself familiarized with the bit ordering. It is the least significant bit is on the right side, the most significant bit is on the left side. And here in this document, the bit is numbered from 1 to 64, whereas in some documents, some of the documents that comes with a tag, they start the numbering from the 0 on the left side to 63 on the right side. But whatever it is, the size of the UID is always 64 bits. So out of these 64 bits, the last byte is always E0, followed by the next byte which gives the manufacturer's code, and the remaining 48 bytes is the number, the serial number. So this is what the standard says, and I'm going to show you how this unique identifier is used in the actual tags made by different manufacturer. So here, this is the document for the M24LR04E document, and if you can see here, so even in this 64-bit, you know, the numbering in this document starts from 0 and goes up to 63. So whatever it is still 64 bits of UID, and as we saw before, the last byte, you would say, depends on how you number this. So the last byte is E0, followed by the manufacturer ID, which is 02 for the manufacturer called ST, and followed by this 48 bits of the unique serial number. The next is I got a tag from Texas Instruments, the TI, and here you can see, so here also, so here the numbering is not mentioned, however, so you can see there are bytes here, so there are 8 bytes altogether. So the last byte is E0, followed by the ID of the manufacturer, which is 07 for the TI, the Texas Instruments, and this also, the remaining 48 bits here, or the 6 bytes here, is also has got something different from the standard. So you have to keep in mind, so the standard covers just a generic structure, whereas every manufacturer can have their own, the manufacturer specific or the product specific information. So in this TI tags, the 6th byte, this byte is used to indicate the type of the tag. So you can see in this example, so this can tell whether it's a plus tag. I've not got any of these tags. I do have probably a standard IC, which I'm going to use it when I start showing you the commands on the actual device. So here the serial number is just the remaining, the 40 bits here. Next, I've got a tag, a document of a tag from NXP. So here also you can see the last byte having E0 followed by the manufacturer's ID, which is 04, and just like the TI tags, the last 6 bytes is divided into the serial number and the IC type. I think 01 here indicates it belongs to IC of a particular type. Probably can also have a 00 or a 02. So this byte is used to indicate what type of the tag it is. So by just reading the 64 bits of unique identifier, you can find out who is the manufacturer, and if the manufacturer is 04, that is NXP, so you can treat the next byte giving you the IC type, and the remaining 5 bytes giving you the serial number. The next important feature is the application family identifier. So this tells what type of application the tag is going to work with. So you can have various tags near the VCD, but the VCD can select a tag that belongs to a specific application. The value of the AFI is written using a 1 byte, and it consists of 2 parts, the upper nibble and the lower nibble. So if you scroll down, these are some of the standard coding. Say for example, if the upper nibble is 1, so this indicates the wick or the tag belongs to an application of type transport, and if the wick has got a upper nibble as 2, it says this belongs to some kind of a financial application, and the subfamilies, that's the lower 4 bits, indicate the sub application. So the standard says the 0, I think according to the standard only 0 is used, but again we can put any number you like. So if you are creating an in-house application, so you can put whatever value you want in this AFI. Now the document also says, so the AFI is not a mandatory thing. So you can see here it says the AFI is an optional. So you can have a tag which does not support AFI, and also the AFI can be written and it can be completely locked from modification. So whether the AFI is available or whether it is lockable, all those things depends on the type of the tag. So let us see now how this AFI is implemented in some of these tags. So if you look at M24LR, so this has got information about AFI, so that means this supports AFI. So likewise in TI tag as well, there is information about AFI. It says this supports 64-bit UID, DSF ID and AFI plus. So the SL2 tag mentions this also supports the application family identifier. So this flowchart here explains how the tag handles a request coming to the AFI. Now some of this information here relates to a command called inventory, which I'm going to explain probably now in the next video. So what you can see here is when the VCD request for all the tags belong to a specific application identifier, the tag compares, and you can see here, so when the tag AFI matches what is requested by the VCD, the tag will answer for such a request. If the tag's AFI does not match with what is requested by the VCD, the tag will not answer at all. So it says basically the tag answers only if the application or AFI matches what is stored within the tag. The next thing is the DSF ID. Again, okay, this is a byte value, and this tells us what is the structure of the data in the WIC memory, and this is completely decided by the application. And again, as the documentation says, the DSF ID is optional, and if the tag does not support, it should just return the value 00. So after that, we have got the CRC. You come across this CRC in every command. So every data that is exchanged between the VCD and the WIC, and the WIC and the VCD, that's in the request and response, there's always a CRC value present. So this is a 16-bit value, and which is computed using the standard which is mentioned here. And also, if you scroll through the end of the document, there is a C program that shows how to compute the CRC16 value. So you can, I have used that algorithm, and you just have to convert that. It's almost it's almost it's a C program, so there is no conversion required if you want a C program, or if you want to convert that to a Java or a VB.NET, then you have to convert that to the respective language. And most readers or VCDs, they automatically generate this CRC value, so we don't have to worry about programming for the CRC. The next thing is the organization of the memory. So all WIC or the tags, they have the memory, and they come in different sizes, but the documentation says you can have up to a maximum of 256 blocks, and the blocks size can be up to 256 bits maximum. So this can be either say, it says the maximum value, probably it can be 1 byte or 2 byte or 3 byte, or up to, say for example, 32 bytes maximum. So if you put all this together, the standard specifies the maximum memory capacity as the 8 kilobytes. And it also says each block of memory can be read and written, and it can also be locked as well. So let us see how this the WIC memory is organized in these three tags. So in M24LR04, that dynamic tag. So the memory is organized like this. So this has got 4 sectors, and plus it also has got some additional memory here, and each sector, as the documentation says, has got 32 blocks. And if you just scroll down this document, you can see the memory layout here. So it has got, altogether it has got 128 blocks, and each block is 4 bytes. So this is the memory organization of this particular tag. The next is the TI tag, and here the memory is organized into 64 blocks here, and each block has got 32 bits or 4 bytes. And the next is the SL tag, and this has got altogether 32 blocks. So starting from 0 to it's actually 0 to 28 blocks, plus it has got some the remaining 4 blocks carrying different information here. And so this is organized as 32 blocks, and each block has got 4 bytes. So what the standard says is a block size, or the maximum number of blocks you can have, is 256. It is because when you see the instruction, the block is addressed by using 8 bits, and 8 bits can go up to 0 to 256, 255. So that's the reason, I suppose, the maximum addressable block in this standard is 256. And also here the block can go up to 256 bits. So what we have seen so far in all the 3 tags, each block is a 32-bit long, or a 4 bytes. The next feature that is described in the documentation is the lock. So each block can be either locked or without locking. So lock here means whether you can change the content of the block, and as the documentation says, the lock is indicated by just 1 bit, which indicates either locked, which is 1, or not locked, 0. And this again, I think, is an optional. So it mentions here, so this is like an optional thing. It depends on the manufacturer whether to support the locking or having no locks at all. But if you think in the practical application, so obviously we want the memory to have some kind of a locking mechanism, otherwise the tag will be of no use. If you look at the documentation of these 3 tags we are looking at, so M24LR mentions about locking, but the way the locking is implemented here is different. We have seen the memory structure of this particular tag, which has got 4 sectors, and here the locking applies at the sector level. So we know that each sector in this tag has got 32 blocks. So a single lock bit locks all the 32 blocks. So that is how it is done in this tag. In case of a TI tag, here if you can see the documentation, there is a separate lock bit for individual blocks. So each block can be individually locked or not locked. So likewise, if you go to the next tag, so this also mentions there is a lock mechanism for every memory block. So locking is supported in all these 3 sample tags as well. The next and the most important thing we have to understand is the structure of the various commands and the structure of the various responses, and how the commands are executed, and what makes the tag respond. For some commands the tag do not respond at all. So all these things we are going to see in the next video.